Hi there. So let's see. I wanted to talk about complexity and things that I am now understanding about it. And there's kind of a long story, goes back about 50 years for me. Um, I'll say a few sort of elementary things, and then I want to talk about things that I've just been thinking about recently. So maybe I can show you. Let's go. Um, just to give you some framing for things I've been up to recently. A couple of weeks ago, I posted something called Towards a Computational Formalization for Foundations of Medicine. A few weeks before that, something about formalized mathematics. A few weeks before that, something about biological evolution, something about the nature of time, nested recursive functions, what's going on in machine learning. I will try and touch on all of these things. So this will be quite challenging. But let me start off talking about ancient history. So back in the late 1970s, I was a young particle physicist, and I got interested in the question of, which seemed to me an elementary question of where does complexity in nature come from? And that got me interested in thinking about, I was kind of, my first thought was, okay, I know all this fancy math from quantum field theory and all these kinds of places. I should be able to solve that kind of everyday elementary problem easily. That didn't work out. So I went, this is now about 1981, I kind of started thinking about, well, okay, if we want to make theories for things, what should the raw material for those theories be? And I thought, well, how do we generalize what we have had from mathematical equations and so on to make more general kinds of theories? And so that got me thinking about programs and making theories in terms not of mathematical equations, but instead in terms of rules that one could specify with programs. Now, a convenient feature of my personal trajectory is that starting in 1979, I had built my first big computer system, which was kind of a forerunner of Mathematica and modern Wolfram language. And so I had had some experience in starting from sort of computational foundations and building up to something, in that particular case, being a useful computational system. But that got me into the idea that perhaps one could take things that happen in nature and kind of start from computational foundations and build up from there, rather than doing the thing that one is more used to doing in natural science, which is sort of taking what nature presents one with and trying to kind of reverse engineer what's going on inside. So I kind of started thinking about the theory of all possible theories in some sense, and the question of kind of what one could get from simple programs. And the question that then arose was, okay, so if one just looks at simple programs, say picked at random, what do they typically do? I didn't have a good name for that field at the time. In recent years, I've tended to call that field ruleology, the study of simple rules and what they do. And I now view ruleology as kind of a very foundational science, perhaps sort of in some dimensions, the most foundational science. Okay, so what does one do in ruleology? Well, let me, I studied a lot. I wanted to come up with simple rules that I could study. I studied a lot cellular automata. What I actually found out after I'd invented them for myself were called cellular automata. You've probably all seen this. I hope you have now, 45 years later, but I'll go through it anyway. And I'd like to tell you a little bit about the kind of journey of discovery, because I think it's relevant. This is a simple cellular automaton. It's a bunch of rules that say, if you have a line of black and white cells, it tells you what color to, what just happened here? Are you still seeing my screen? You're seeing a cellular automaton on the screen. Yes, no?
Yes.
Yes. Yes, good. Okay, good start. Okay, so let's see, what does this thing do? Well, let me just run it for a few steps, let's say 40 steps. And let's say, show mesh there. Okay, so this is what happens if we just apply that rule, starting from a single black cell, that rule at every cell, at every step, that's what we get. Okay, well, the thing I was at first interested in was a phenomenon that one can call sort of self-organization. How do you go from apparent randomness to some level of order? And so the sort of first experiment that I tried was the following one. Let me show you. Um, let's say something like this, that, let's say, and if we look at these solid automaton rules, there are 256 possible rules of this general type. And let's just do the kind of computer experiment. We're kind of pointing a computational telescope out into the computational universe and seeing what's out there. And let's take a look. This is now starting from random initial conditions. And so what we see is that, okay, in some cases, we start off with a random initial condition, immediately everything dies out. Other cases, a few things survive. It's kind of like a filter that's keeping just a few elements. Other cases, something more complicated happens. These are cases where even though we start off from something that we chose the black and white cells completely randomly, we still get some kind of organization, some kind of structure. I thought this was pretty interesting, and I studied this a whole bunch, and you can use dynamical systems theory to understand that there's kind of like a strange attractor and so on. These kinds of things are like fixed points or limit cycles or whatever else. Lots to study here, and I spent some time doing that. But I had also was aware that one could look at what happens with simple programs starting not from random initial conditions, but from simple initial conditions. But I thought that's not going to be terribly interesting. After all, the program is simple, the initial condition is simple, it's not going to do anything terribly interesting. And that was my intuition, because that's what we expect from something like engineering, where if you want to make something complicated, you have to go to lots of effort to make it complicated. Well, I knew, for example, this is an example of, this is rule 90. This is kind of, we can think about this mathematically as binomial coefficients mod 2, and this makes a nice nested kind of pattern. I knew about things like that. Okay, but my intuition was simple initial conditions, not going to do anything interesting. Okay, well, actually, I had even published in, I think it was even in, it was a thing I wrote in Nature, for example, this was in 1983 or so, where the nasty brown spots here come from glitches of film cameras. But anyway, had pictures in it that had sort of signs of what happens even with simple initial conditions, but I didn't pay much attention to it. One day, I finally did the obvious experiment and just looked at what happens with all possible rules, just with very simple initial conditions. Every time Zoom, once somebody shows up, it changes the focus and I can't type anymore. That's okay. Okay, so then let's look at this starting not from random initial conditions where we could see that we got this kind of self-organization happening, but from very simple initial conditions. Let's just run that, see what happens. Okay, so at the beginning, you know, it's doing kinds of things we might expect. It's making stripes, it's making a nested pattern and so on. And then we get down here to rule 30. This is my all-time favorite science discovery. This is just a rule like the ones we've been looking at here. Let me bring it up here. That's the rule, and let's run it, see what it does. Well, this was a big surprise to me. This was not something I expected. It took me a couple of years after I'd first started studying cellular automata to even think to look for this. And once I saw it, well, by the time I saw it, I was somewhat primed to understand what was going on. I realized this is something very interesting. This is something where sort of we put almost nothing in. Very simple rule, very simple initial condition, yet what comes out is something complicated. And for me, this was kind of the discovery of what sort of I view as kind of the essence of, well, sort of the central discovery of rulology and kind of the essence of a lot of understanding where complexity comes from in the natural world and beyond. So that's a picture of rule 30, run a bit longer, starts from very simple initial condition, makes this pattern, which has a certain amount of regularity over on the left. But many aspects of this pattern are, for all practical purposes, completely random. Like we used the center column of Rule 30 as a pseudorandom generator for Mathematica for a long time. We retired it recently in favor of something slightly more efficient that's also based on cellular automata. But the point is that we have this strange intuitional thing that even a very simple rule can do very complicated things. Now, I have to say that I've studied lots and lots of kinds of simple rules, and almost every week I'll be studying something and I'll have a theory that this particular kind of rule can't do this particular kind of thing. And almost always I'll be wrong. I mean, my kind of line for people who are working with me often is something like, the computational animals are always smarter than we are. And I can't emphasize enough how important it is to actually try some of these experiments yourself. I mean, with Wolfram language, we built an environment that makes it really easy to try these kinds of experiments. Just try some of these experiments. We'll talk about a bunch of other kinds of experiments later on a bunch of other kinds of topics. But the point is that until you've experienced this phenomenon for yourself, it's very hard to believe that it's really possible for a rule as simple as that to do something as complicated as this. Well, what can we say about what's going on here? How do we make, beyond just saying, well, what's happening is complicated, what can we say? You know, back in the 1980s, when I was first working on this, there are a number of very good mathematicians who got very interested in this. And they said, look, this is such a simple system to define, we'll be able to crack it. We'll be able to do math to figure out what's going on here. They didn't succeed. After a year or two, they kind of gave up. They said, we have nothing to say here. There's nothing useful we can do. And I think in retrospect, probably my biggest achievement at the time was realizing that the very fact that there wasn't anything one could say using those traditional methods of mathematics was itself the most interesting fact. The fact that it was hard to say what would happen was itself very interesting. So what's the framework in which one can understand that observation? Really relates to two ideas: what I call the principle of computational equivalence and what I call computational irreducibility. So one question we can ask is, how can we characterize what's happening in a system like this? Well, we can say, actually, let me go in a different direction for a second here. Let's ask the question, what's going to happen in the system after 1,000,000 steps? How are we going to find out? Well, if we were looking at something like this, we say, what's going to happen after 1,000,000 steps? We'll be able to figure that out. We'll be able to make essentially a formula that jumps ahead of the actual evolution of the system and figures out what's going to happen. That's kind of what we've gotten used to from mathematical science, from being able to figure out, for the idealized two-body problem or something, where's that planet going to be 1,000,000 years, 1,000,000 orbits from now? We just fill a number into a formula and we get the answer. And so it is with a pattern like this. But the question, and we can think of that as kind of an act of computational reduction, a piece of computational reducibility. We can come in with our mathematics or whatever else, and we can reduce the amount of computational effort it takes to figure out what will happen. The system itself might run for 1,000,000 steps, but we can just use our more sophisticated computation and jump ahead and know what's going to happen. Okay, so the big thing is that in a system like Rule 30, that isn't the case. Rule 30 is, the mathematical proof of this. We can talk about what the status of that is, but let's just say for practical purposes, we can conclude that this system is computationally irreducible. What does that mean? It means, well, if we want to find out what will happen 1,000,000 steps from now, we can just run those 1,000,000 steps and see what happens. But can we jump ahead? The answer is no. This system is doing an irreducible piece of computation. There's no way for us to figure out in advance what's going to happen more efficiently than basically just running the system and seeing what happens. So this phenomenon of computational irreducibility is a phenomenon which is basically saying that the approach we might use in science, the approach we become used to in kind of mathematical science, where we say, we've got the system, we know its rules, now we can jump ahead and see what will happen, that's not something we're generally going to be able to apply in the computational universe of possible programs. Instead, we're learning that sort of from within science, we're learning a phenomenon which in a sense is a fundamental limitation on science, a fundamental limitation on the kinds of things that we will be able to kind of jump ahead and predict and say in advance. So there are many implications of computational irreducibility. I kind of came up with that concept just about 40 years and a couple of months ago in 1984. And I've been amazed at all the consequences that computational irreducibility has had, including some quite unexpected to me. For example, I'm pretty sure that the originator of Bitcoin had read a bunch of things that I wrote about computational irreducibility. When I was thinking of it as a limitation on science, I had no conception that it might end up being the inspiration for burning immense amounts of power to kind of have some proof of work for a cryptocurrency. I also in thinking about computational irreducibility is important if you're interested in things like AI ethics and trying to figure out, can we know in advance what the AIs are going to do, and can we be sure that they're going to do the right thing, so to speak? Another direction, another branch of the application of computational irreducibility. Another branch that I'll try and talk about here is the derivation of the fundamental laws of physics, which is something that I had never imagined was possible, but we'll talk about how that seems to be working. But if we drill down, what's the source of this phenomenon of computational irreducibility? Why does such a phenomenon exist? Well, here's the way to think about it. If a system is going to be computationally reducible, it means that we can, in a sense, be smarter than the system. Well, we can think of both the system and what we do in our brains as being the doing of a computation. And so the question then comes, is the computation that's going on in something like Rule 30 a simpler computation than the computations that we can achieve with things like our brains? Well, one of the things that I came up with in the early 90s is this thing I call the principle of computational equivalence, which says that basically above some very low threshold, all systems are equivalent in the sophistication of computations that they do. So in other words, we don't get to be sort of smarter than Rule 30. We are simply equivalent in the sophistication of computations we can do. So that idea is kind of a strengthening of the idea of computation universality and so on. And one of its implications, one of the implications of the principle of computational equivalence, is that if you just go out there in the kind of computational universe, most systems you see will be as computationally sophisticated as possible. So for example, here's an example of another cellular automaton, same type as I was showing, except this one happens to grow only on the left, because that's the way its rules are set up. And you can kind of see it doing its thing. What's interesting here, if we let this thing run a bit longer, we can kind of try and predict what it's going to do. Let's run it for 1,500 steps. You might be able to see these little localized structures running around, and we might wonder what it's going to do. And it's kind of a computational irreducibility story. What's it going to do in the end? There's no finite computation that will guarantee to tell us what this will do in the end. In this particular case, I think after about 2,500 steps, this particular rule, this particular initial condition, it resolves what it's going to do. But this is an example of a case where let's run this starting from a random initial condition. Let's say, let's do that. Okay, so if you can see that, I might have to make a higher resolution version. It's got a coarser version of this, but you can see that. You'll see that it starts off from a random initial condition. It really is very much organizing itself, but it's organizing itself to make all these structures that are running around. And you might imagine that you could think of those structures as being like signals that are propagating in some kind of logic circuit. And yes, indeed, one can show that this particular system is capable of emulating any computer, doing any computation, being a universal computer. And this is something where it's sort of a prediction of the principle of computational equivalence, that if you look out in different kinds of systems, even as soon as you see behavior that seems complicated, it will turn out to be, among other things, computation universal and also show computational irreducibility. So as an example of, I have one here, I have it here. As an example, a few years ago, I was curious about the same kind of thing for Turing machines, and the very simplest Turing machine that doesn't have obviously simple behavior is this one here, still a very simple rule. You run it, it does things like this. And so the question was, is this Turing machine actually capable of universal computation, as the principle of computational equivalence suggests. And so as another kind of piece of evidence for the principle of computational equivalence, I was happy that a young chap in England rather quickly won this prize that I put up for establishing whether or not this particular Turing machine is universal, and he showed that, yes, it is in fact computation universal. So this is kind of the underpinning of what's happening in these systems, is this phenomenon of computational irreducibility, and that's a consequence of the principle of computational equivalence. Okay, so we can then go and there's a lot of kind of different intuition that we get about things by looking at by thinking about computational irreducibility and so on. Let me maybe many different directions I could go here. Let me talk a bit. I could talk about physics. I could talk about biology. I could talk about mathematics. Maybe I should talk about all of those. Let's see. Maybe I will start off by let me start by talking about physics. So one question: once one's seen Rule 30 and its friends, one of the things that one starts wondering is, okay, there's a very simple rule that can do very complicated things. What about our physical universe? Could it be the case that our whole physical universe is actually based on some very simple underlying rule, and we're merely seeing the consequences, the kind of computationally irreducible consequences of the application of that simple rule? Well, it was clear from a long time ago that cellular automata, for example, or Turing machines weren't going to be the appropriate underlying stuff to make something like physics. But I started thinking back in the 1990s, and then finally kind of realized how it would all fit together in 2019, about how to think about sort of what's underneath physics as we know it. We have a huge leg up in studying physics because 20th century physics got a long way. And so we're able to take the results of 20th century physics and try and connect with those. We don't have to go back to the beginning, so to speak. Actually, one of the things that is sort of a story of physics from antiquity on is this question of, is the universe discrete or continuous? People argued about that in antiquity, and people didn't know the answer. By the end of the 19th century, it had become clear that, yes, matter at least was discrete, made of discrete molecules. And then became clear that light was also could be thought of as made of discrete photons. People at the time, beginning of the 20th century, most physicists assumed that space would turn out to be discrete as well. And they didn't actually publish much about this, but they all, Einstein, Bohr, Heisenberg, they'd all made models of discrete space, it turns out. None of them could make it work. The kind of mathematical structures that they had at the time, they couldn't make their thinking about these things consistent with what was known about relativity, and they kind of gave up. And so for a long time, it came to be assumed in physics that space was just this background in which you put things at different places. So the starting point of my efforts in understanding fundamental physics come from the idea that space isn't just a background, space is made of stuff. In particular, we can think of space as being made of kind of atoms of space. The only thing we know about these atoms of space is how they're related to each other. So, for example, let's see, we might have a little network of atoms of space here, and they have certain relations. We make a graph, a network. Actually, it's convenient to think about hypergraphs where we can relate not just two nodes, but any number of nodes in a hyperedge. But in any case, this is what we think of. We think that space and everything in it is just this giant network of relations between atoms of space. And then the question is, well, okay, and that means that, for example, all the things we are familiar with, electrons and photons, all those kinds of things, just have to be features of the structure of space. We just saw that cellular automaton that had all those little structures running around in it, Rule 110. That kind of gives one some sense of how one might get things like particles emerging from something in which there was at first was just some kind of uniform structure. Okay, so a bit like a cellular automaton, we can ask, so how would this network that represents space and everything in it, how would it evolve? Well, you could just imagine that there's some simple rule that just says whenever you see a piece of network that looks like this, replace it by a piece of network that looks like that. Well, let's try running that rule. Here's what you get. Starting from that very simple initial condition, you start building up this more and more complicated network. Keep going, you get this kind of complicated structure, and so on. Well, what we're doing here is we're essentially growing the structure of space. And in some cases, it's very simple to see what happens. There's a particular rule where it literally knits a kind of two-dimensional pattern like this. In more generality, you can knit all sorts of different complicated structures. And the point is that what's happening is we're kind of growing space out of discrete elements in sort of the same kind of way that you make a fluid like water from lots of discrete molecules bouncing around. But here, there's no bouncing around going on. It's just the structure of the network that, on a large scale, we can think of as representing the structure of space. For example, there are many features of this that aren't that are complicated. I mean, this network doesn't have any particular dimension. It doesn't, the fact we can sort of try and estimate the dimension by just saying start from a particular node and just go successively to nodes that are neighbors of that node, neighbors of the neighbors, neighbors of the neighbors, et cetera, and ask if we've gone R steps, how many nodes have we got in that ball that we formed going R steps away? If we say they're about R to the D nodes in that ball, then we say the thing is behaving like a system with dimension D. And in fact, in our belief about the universe is that it started infinite dimensional and gradually kind of cooled down to being the 3 dimensions that we see today, probably with some fluctuations, and that's something that we hope will be experimentally observable, is dimension fluctuations, parts of space that are like 3.01 dimensional and so on. There's a difficulty in dealing with that kind of thing because the mathematics of calculus and even geometry for spaces that have dimension as a dynamical parameter like that is completely unworked out. And so we're having to sort of build what we're thinking of as infrageometry and infracalculus to try and deal with those kinds of things. But in any case, let's see if I can find the right thing here, sorry. So if we look at we can look at sort of the universe growing by applying these network rewrite rules. This is a sort of simple version of the very, very beginning of the universe, progressively applying these rewrite rules to grow this larger and larger network. And the fact that things are like wobbling around on the screen is a pure artifact of the rendering of this model universe. The only thing that matters to the universe and its occupants, so to speak, is the connectivity of this graph. Well, if we go much later in the history of the universe, we can kind of set up something which is sort of an approximation to the structure of space as it might be far into the future from what I just showed. And in this particular part of space, we have 2 very tiny black holes. And what we'll see here is the dynamics, according to network rewrite rules, of 2 little black holes in the universe. And a lot of what we see is kind of space wobbling around. The structure of space is dynamic. But what we'll see is that there is a sort of force of gravity that pulls these 2 black holes together, and eventually they merge. And if you look carefully, you'll see little ripples going out that are gravitational waves. And indeed, what we see agrees with what we expect from general relativity and what's actually observed. Conveniently, black holes are one of those rather scale invariant things where you can look at one that's really tiny down at the level of sort of individual atoms of space, and it'll have many of the same characteristics as a really big one. Okay, just to give some indication of a different direction, and I don't want to go into this in too much detail, is the question of, just to say that what's happening here is we have sort of the emergence from sort of this irreducible set of computations going on at the level of individual atoms of space and network rewrites and so on. What we're seeing is that on a large scale, much like molecules in a fluid on a large scale give you fluid dynamics, on a large scale, instead of getting, for example, the Navier-Stokes equations of fluid dynamics from molecular dynamics, what you get in the case of network rewrite rules is not that, but instead the Einstein equations for the structure of space-time. So that's kind of how something understandable emerges from something that is full of computational irreducibility. It's very much the same story as what's happening in fluid dynamics. Well, let me mention a little bit about quantum mechanics, and then I want to come back to talking more generally about the derivation of physics, and then we'll talk about mathematics and biology and other things. Let's talk about quantum mechanics. One of the questions is, you've got this network, and you've got this rule for rewriting the network, and that rule might apply in many different places on the network. So then you have to ask the question, well, which place should you apply it? And the thing is, you don't know which place to apply it. So you can imagine applying it in all possible places, and that generates many different paths of history. So let's look at a kind of picture of how that works. This is, should be, let's try it again. A bit confused here. One more attempt. There we go. That looks better. Okay, so now we're going to trace not a single possible sequence of rewrites, but kind of all possible paths of history. We'll see that that one was unique. That one had 3 possibilities, more, and so on. So what we're building up is many different paths of history. And actually what we see here, the little purple lines, represent kind of relations between the paths of history. And we can kind of build up a space, we call it branchial space, the space of branches that represents kind of the interrelations between these paths of history. Well, in a sense, we already know that the essence of quantum mechanics and its distinction from classical mechanics, in classical mechanics, kind of definite things happen. You throw a ball, it goes in a definite trajectory. In quantum mechanics, we imagine that there are many paths that are followed, and we only get to observe sort of the aggregate of some of those paths. Well, in these models, we have that in an incredibly direct way. We have what we call multi-way systems being formed, where we have many different paths of history, many different possible rewriting sequences, and the kind of aggregate of all those different paths, we form this kind of space of the relation between those paths. And we can see. We can look at kind of how that works. Let's see. There we go. So this is a very simple example of a multi-way system. This is just based on rewriting strings. And we see that there are sort of many paths you can follow depending on which rewritings you do. And kind of the idea is that those paths correspond to possible paths of history of the universe. Now, one thing that's a little bit mind-bending is that what we have to realize is that our perception of what's going on is based on kind of us as fairly coarse observers of the system. So in the case of physical space, just like as in the case of a fluid, we are large compared to the atoms of space or the molecules in a fluid. And so we perceive kind of the continuous fluid as being the thing that is the aggregate of lots of different molecules. In quantum mechanics, what's happening is that our minds are actually spanning many paths of history. So we get to perceive things in these kind of patches of branchial space. And that's kind of the beginning of the story of quantum mechanics. Okay, well, I mentioned something about sort of being able to derive the laws of physics. And one of the things that is sort of a big surprise in a sense. Well, actually, let me mention something about multi-way systems, first of all. Multi-way systems show up all over the place. So, for example, you can think of a game graph as being a multi-way graph. So this is kind of a simplified version of tic-tac-toe. We have different kinds of moves we can make. The thing we make, the graph that we make here, is a multi-way graph. And we can keep going, and eventually we'll have something which shows all possible sequences of moves in this game. And maybe if we're doing a version of the game, we could score the game, and we could have, I think this is a thing that shows what wins, what loses in tic-tac-toe. That's another example of a multi-way graph. Multi-way graphs show up all over the place. Another place where multi-way graphs show up is in thinking about mathematics. Let me show you an example of that. Oh, actually, let me show you a simpler example perhaps first. This is just a very a system where you're just aggregating cells onto a cluster is kind of the Eden model of growth. You build up a cluster like this, but what I showed you there was just randomly adding a cell. And it's very typical in systems to think about, well, what if we just sort of randomly run a sequence of moves? Multi-way graphs are the story of what all possible sequences of moves do. So this is the multi-way graph for this Eden model, showing all possible moves and all possible outcomes. And you build up a whole complicated structure of branching as two different possibilities occur and merging as two possibilities that were different end up evolving to the same state. And there's a whole elaborate theory of multi-way graphs and multi-way systems, and it connects to lots of interesting areas of mathematics and other things. But multi-way graphs show up all over the place. I'll show you one more example, which maybe we'll come back to later, which is in mathematics. So we can think of mathematics as we can think of mathematics as defining sort of axioms in mathematics as defining relations between expressions like these. Well, we can make a graph that shows how those expressions are related to other expressions by virtue of that axiom, by that rule, so to speak. We build that up, and we're getting a multi-way graph here. That is a multi-way graph showing the relations between different mathematical expressions here. We can keep going, we can keep going. We can have we'll build up a rather complicated graph. If we wanted to prove that two mathematical expressions are equal, what we want to do is we want to show that there exists a path in this graph that goes from one of those expressions to the other. So a proof in this case is a path from one place to another. And we can think of this just as we can think in physics, in quantum mechanics, for example, of the paths of history being laid out in branchial space. We can think of these different kind of possible proof paths as being laid out in metamathematical space in kind of a foundational idea for how mathematics works. We're sort of interested in the limit of mathematics as things go to infinity. You know, in the literature of mathematics as it exists today, there are maybe 3 or 4 million theorems that us humans have written down. But we can imagine what's the limit if we were to derive all possible theorems? What is the structure we get? That's kind of the limiting metamathematical object. Okay, but back to physics and multi-way systems in general. One of the things that is very kind of mind-bending to think about is imagine that we find this rule and it successfully reproduces all the things we know about physics. We kind of hold up this rule, we say, this is the rule for the universe. This tiny little rule does all these things. The next question is, why did we get this rule and not another one? And I wondered about this for quite a while until I realized that the answer is kind of obvious. The answer is the universe is actually running all possible rules. The universe is in effect, just as we said, we're taking a particular rule and running it in all possible ways, and that's what's giving us quantum mechanics. Well, actually, we can think of the universe as running all possible rules. Well, we might think that's just a huge mess. How could we ever sort of say anything about a system that's just running all possible rules? Let's see. But actually, there's a lot of structure. So, for example, let's imagine that the rules we think about are Turing machine rules. There's the rule for a Turing machine. There's what the Turing machine does. We can make a multi-way Turing machine that has multiple moves from any given state. We'll build up a multi-way graph from it. But now let's consider the case where we look at all possible rules for all possible Turing machines. What we'll build up is the structure that has states of Turing machines and edges corresponding to each possible rule for a Turing machine. What we'll build up is this thing that is kind of this, that limits to this structure that is a structure of all possible moves for all possible Turing machines. And as we can plainly see from these pictures, this is a thing with a lot of structure. It's, even though in a sense anything can happen, there is an entanglement between different possible things that can happen that makes the whole structure extremely non-trivial. So this object that is the entangled limit of all possible computations is the thing that I call the Roolead. The Roolead is kind of this unique object that is, in a sense, encapsulates all possible computation. It is the entangled limit of all possible computations. And that is the thing, that's a unique object. It's an object, once you define the idea of computation, you inevitably have the Roolead. There's no, well, I might have the Roolead or I might have something different. No, you inevitably end up with the Roolead. So now the question is, well, how does that relate to, for example, physics? Well, what you realize is that if the Roolead is sort of everything, then we as observers, we must be part of the Roolead. We are observers of the Roolead operating inside the Roolead. So now the question arises, what do observers of the Roolead perceive about the Roolead? Well, it depends what those observers are like. And the big result from the last few years, as far as I'm concerned, is that you need only very light assumptions about what observers like us are like to conclude many things about how those observers will perceive the Roolead. Turns out the two most important things are that we are computationally bounded and that we believe we are persistent in time. So, at every moment we are made of different atoms of space. So in principle, we might not have any we might not be persistent in time, but we feel that we have a continuous thread of experience going through time. We believe we are persistent in time. We also are computationally bounded, even though what's happening at the lowest level in sort of the microscopic structure of the universe is full of computational irreducibility. We are completely unable to reach that. We only perceive this kind of coarse kind of approximation that is our sort of computationally bounded observation of all of that computational irreducibility. So the thing so the question is, how does it come to be that the laws of physics are depend on sort of how you are as an observer? Well, there's if we look at 20th century physics, there's sort of three big theories in 20th century physics. There's relativity, general relativity, the theory of gravity, theory of space-time, there's quantum mechanics, and there's statistical mechanics, whose main feature is the second law of thermodynamics, the law of entropy increase. And people had imagined, even from the mid-1800s, that the second law of thermodynamics might not be something that was just a kind of wheel-in feature of the universe, that it might be that the second law of thermodynamics could be derived from the underlying kind of underlying laws of mechanics. And so, the typical picture is you have a bunch of balls in a box, and they're at first arranged in a very orderly way, but it tends to be the case that those balls wind up having, being arranged in this kind of random way, or what appears to us to be a random way. And that's what the reason we say that sort of entropy increases is because we say the number of states of the system, the entropy is the log of the number of states of the system that are consistent with what we know about the system. And in this case, all we can say about the system, well, it looks kind of random and there are this number of balls in it. We don't get to say anymore. And so there are more states of the system consistent with that than if we could say, well, we have all the balls are in this array in one corner of the box. So in any case, if we take something like this and we ask what's the essence of what's going on, what leads to this generation of randomness in the system, what it really is not that. If we were to look at the system, we would find that we could just reverse what happened here and we could go back to this initial condition. The problem is that it is computationally irreducible to do that. So we can take a simpler case. We can simplify this. So that's a space-time picture of what I was just showing there. We can kind of simplify what's going on. We can make it discrete. We can make it in one dimension. And we can eventually end up with something that looks like this, where we're starting off from just a very simple initial condition there, and it's sort of getting ground up to produce this apparent randomness. This thing is reversible in the sense that given any state of this system, we can uniquely go back and find that initial state, at least if we could run the computation well enough. And that means if we look here, as we go forward in time, things will sort of grind up into randomness, and we go backward in time, it will similarly grind up into randomness. The question is, if we're just shown something that looks random to us, can we tell that it comes from something simple? And the answer is, well, no, we can't. If we're computationally bounded observers, we cannot do that irreducible computation necessary to determine what that initial condition is. So in a sense, the second law of thermodynamics is a story of the sort of encryption of the initial conditions by the dynamics of the system. And it's a story of the interplay between the computational irreducibility of the underlying dynamics of the system and our computational boundedness as observers. The reason we believe the second law is true is because we are computationally bounded observers. If we were not computationally bounded observers, we wouldn't believe the second law. If we were, there's a common picture of sort of the heat death of the universe, that in the end, the whole universe will just be full of things that seem kind of random. Yes, they will seem random to us, but to a different kind of observer, they will seem to have the sort of all of the future of all of the detail that is the way we are now. So there's a place where the laws of physics are determined by our character as observers. Well, it turns out that the same thing seems to be true for both general relativity and quantum mechanics, that from those very loose assumptions that I gave you about what observers like us are like, you can then derive not just roughly, but exactly those particular laws of physics. I think that's quite exciting, that in a sense, the laws of physics are necessarily the way they are if we are observers of the kind we are. There's a great deal more to say about that, but I wanted to go on and talk about some other things here. We've kind of, what we're seeing in that case is that underneath there's computational irreducibility, but at the top, there are laws of physics we can talk about, like general relativity. In other words, as a certain kind of observer, we are kind of skating over the computational irreducibility. We are finding kind of a slice of computational reducibility within all of that computational irreducibility, and that's what we're making these laws out of. And what we'll see is in a lot of other kinds of systems, sort of the story of complexity ends up being a story of computational irreducibility, and the story of laws that live on top of that is a story of kind of slices of computational reducibility on top of underlying computational irreducibility. And I know for a few cases, and I'll talk about biology, I'll talk about machine learning as examples where we can kind of see a little bit more about what's going on. I don't know about the case of economics. I'm really interested in that case. I don't know about that case yet. But to mention the case of mathematics, actually, what are underneath this kind of whole network of theorems is a big story of computational irreducibility. What is the emergent, larger scale kind of, what are the laws of mathematics? What are the global laws of mathematics? I would say that one of the most significant, well, there are two things about mathematics that are obvious. One is that it's hard, and the other is that you can do it at a high level. What does that mean? The fact that the fact that it's hard is a consequence of computational irreducibility. The fact that, to prove a theorem that you care about might take sort of huge amounts of computational effort. Actually, I just wrote about this very recently. There's a, let's see, there is a particular proof that I made. It's actually probably the only example of a proof that was found by automated theorem proving that was not already thought to be true. It's a proof about the simplest axiom for Boolean algebra. And the proof of this is very long. There it is, a couple of pages. This is sort of a sign of computational irreducibility in action. This proof is long. If you kind of draw out the relations between the lemmas that you need to prove this proof, it's a long thing. And you can kind of see, let's see if I show you. There are representations of this proof. This is kind of different steps in the proof. I think this proof, if you unroll it, it's about 83,000 steps long. And this is kind of a sign that it is possible to do this proof, but it is difficult, is kind of a sign of computational irreducibility in action. But the thing that I wanted to mention is that it is not the case that whenever you do mathematics, you have to grind down to do all of these very low-level axiomatic kinds of proofs. The surprising thing about mathematics is that it can be done at a high level. You can talk about something like the Pythagorean theorem and you can just be discussing triangles in terms of geometry and the Pythagorean theorem without having to look over your shoulder and say, this is the axiom that I'm going to use to define real numbers and so on. And so you can ask sort of, how does it come to be the case? Let me show you the Pythagorean theorem. Well, I can show you, let's see, what's this? This is the mathematical structure of mathematical space for some simple propositions about Boolean algebra. And you can kind of build up the structure of that space. There are many, many, many theorems that you get, most of which aren't ones any human cares about. Those two red dots are the only two theorems that humans care about from this whole collection that exists in mathematical space. But what we'll be able to see here, let me try and show you an example. Okay, that's the theorem network from Euclid. But this is, okay, that's the Pythagorean theorem represented at its lowest level. That's the structure of the proof of the Pythagorean theorem starting from axioms of set theory and so on. It's very complicated. But most of the time, you never have to worry about this. Most of the time, we can do mathematics not worrying about this kind of machine code level. What's it like? It's like the fact that most of the time we can do fluid mechanics without kind of thinking about molecular dynamics. We can just think about the fluid as having some velocity and so on. We don't have to drill down to the molecular dynamics. So an important fact about mathematics is that higher mathematics is possible. We can talk about the Pythagorean theorem without having to grind down and talk about all the underlying axioms. And that fact that higher level mathematics is possible comes from the same place that the fact that fluid dynamics is possible, the fact that we can talk about space and so on. It's the fact that as mathematical observers, we have some of these same computational boundedness constraints, and we get an effective theory of mathematics that can talk about things like the Pythagorean theorem without grinding down to the lowest level. That's a case where we've where we found higher level laws. There are other higher level laws of mathematics that have a more bite, actually, in some sense. There are things like being able to say that metamathematical space, like physical space, is somewhat homogeneous, which means that you can translate yourself from one place in mathematical space to another. One place might be the place that corresponds to algebra. Another place might be the place that corresponds to geometry. The homogeneity of mathematical space is telling one that there will be dualities, correspondences between different areas of mathematics. Just to get a bit more wild, you can make there's many things are analogous. So, for example, black holes in physical space turn out to be analogous to decidable theories in mathematical space. Black holes are places where time stops, where at least one kind of them is, where you have a path and that path is of limited length. Well, in mathematical space, the analog of a limited length of path is a proof of bounded length. And that's what happens when you have decidable theories. So, okay, in any case, that's it's kind of a little bit of a picture of this underlying computational irreducibility, which is quite ubiquitous. And then the question of, are there higher level laws that work for observers like us that allow us to do things like do mathematics, for example? Okay, let's talk about biology for a minute. Maybe I'll talk first about biology, then I'll talk about machine learning, and maybe I will talk about something I was recently doing about medicine. Let's see, what's biology? Gosh. All right, here we go. Okay, so we're interested in studying things like biological evolution. And recently, this is stuff I did about 4 or 5 months ago. It's stuff that I started to try to do in the mid-1980s and didn't have the right intuition and didn't manage to do it. And I tried again last year, particularly informed with intuition from machine learning, and discovered that actually now I had something I think rather interesting to say. So this is a very minimal model for biological evolution. You imagine that you have here this is again a cellular automaton, actually. I've studied many other kinds of systems than cellular automata, but here we're back to cellular automata. Here are its rules. And here, starting from a simple initial condition, this is what it does. It grows for a few steps, and then after, I don't know, 50 steps or so, it dies out. That's its rule. So imagine that we're making mutations to that rule. we're changing the outcomes in the rule. We're changing bits in the rule. Well, now let's say, let's keep changing bits in the rule, always trying to make the thing live longer, but not an infinite time. Well, we find out there's a picture that shows kind of each red dot is an attempt we made to, with a random mutation we did that tried to make the thing live longer. Most of the time it didn't work, but sometimes there's kind of a breakthrough and we succeed in getting the organism to live longer. So we can look at the sort of sequence of breakthroughs that happen. Here they are. And this is kind of like we're seeing paths in biological evolution. Now, if we roll the dice differently, we'll see different paths. We'll see different kinds of different approaches that the system takes to living a long time. Each of these represents sort of a different set of ideas about how to live a long time. And it's kind of reminiscent a little bit of the fossil record that we see these different paths that sort of biological evolution took to solve the problems of the struggle for life, so to speak. And we're seeing that in this very simple case here. Well, we can now go on and start to think about things like multi-way systems. So what I showed there was kind of what we get from particular rolls of the dice about what mutations occurred. But we can make a multi-way graph that shows all possible mutations that can occur. This is for a slightly simpler case than the one I just showed you, but this is showing all possible organisms, so to speak, with all possible mutation paths. So we can think of this as kind of a very microcosm of the tree of life, so to speak, where we're seeing, you know, one class of organisms over here that figures out what they're going to do in this way, another class over this way, and so on. We can look at a slightly larger version of this. We could look at, let's see if I have one here. Yes. This is a larger version with more organisms, more different ways to do things. Now, we can also actually think about, just as an analogy between different fields, we can think about the multi-way graph of all possible mutations. But what the fitness of what sort of the things that drive fitness in biology, they are essentially driving us in a particular direction on this multi-way graph. They are producing what we might think of as foliations of this multi-way graph. They are determining that if the goal is to make an organism that lives as long as possible, this is the multi-way graph. This is the way that we'll arrange the multi-way graph. This is the way that we'll make slices across the multi-way graph. And so what happens is that it's a story very similar to these other stories we've told. What's happening is fitness functions are kind of like observers. Fitness functions are computationally bounded ways of kind of slicing this multi-way system. We can choose different kinds of fitness functions. Let's see if I can find one here. Well, this is based on, I think, aspect ratio patterns and things, and we can make sort of a fitness function that determines how that works. And we can look with different fitness functions. We can say, well, this is, what is this one? I think this is, oh gosh, I don't remember which fitness function this is, but this is the relative abundance, effectively, of different organisms as a function of time with one fitness function. We could ask questions like, okay, if we change the fitness function part way through, what happens to these different organisms? This is a continuous change of the fitness function, and we're effectively changing the foliation that we're making of the multi-way graph and determining which organisms will emerge, and that's the picture of what you get from that. And you can get, depending on what's happening with these fitness functions, these are jumps in the fitness function. You'll see different kinds of successive evolution paths for these creatures. But the point is that what we're seeing is that biological evolution, in a sense, is this coarse-grained approach to this multi-way graph of possibilities. And most of what's happening, most of the detail of what happens in the organism is a story of computational irreducibility. Most of that detail of all the elaborate patterns that you see are a matter of computational irreducibility. The natural selection is just providing this kind of coarse-grained determination of which piece of computational irreducibility wins and which does not. Well, if you look at these different, these are a few kind of winning organisms that live a long time. One thing that's interesting about this is when we look at this and we say, well, why did these organisms live a long time? It's really hard to answer that. That one in the middle lives 151 steps. Maybe you can see some kind of mechanism there. You can sort of start to explain why this organism lives 151 steps. But this organism here, 308 steps, it just flaps around for a while and eventually it dies out. There's nothing much you can say about what's going to happen. It's kind of an irreducible computation to find out what will happen. It happens to run for 308 steps and then it dies out. So what we're seeing here is in biological evolution, we're kind of taking this computational irreducibility that exists as sort of the raw material for these organisms, and natural selection is coarsely kind of picking particular paths, the particular cases that it's going to make use of. Okay, well, let's turn to machine learning. It's been rather mysterious. I mean, it's always been quite mysterious why machine learning works. And let's see. And so I was trying to understand that. I can talk about lots of different kinds of machine learning. I even wrote a little book just a couple of months after ChatGPT came out about ChatGPT and why it works, and that's a different story, and it relates to things about what we understand about human language and so on. But I'm just going to talk about much more generic, simple machine learning. This is a neural net. It has an input X. It has an output f of X. This is the function f of X that we're getting this neural net to produce. And we've picked the weights based on the color. The colors here represent the weights in the neural net, so that if we feed in a value, let's say minus 0.5, we'll get these different activations. We'll get the value 0. If we feed in plus 0.5, we'll get the value 1 there. So that's a sort of typical neural net. Pretty complicated to see how it works. You know, if we plot out the activations as a function of the inputs, they make this very complicated pattern. If we look at what happens when we train the neural nets, we can see we're gradually sort of tuning these weights in the neural nets to get it to learn the function we want. If we look at sort of the progression of those weights, it's again quite complicated. So what's going on? Well, I was trying to find sort of a minimal model. This is now just about 3 months ago. I'm trying to find sort of a minimal model for what's happening in machine learning. It turns out you can simplify it a lot. First of all, you can say we don't need to have all of those weights that are all of those neurons connected in this arbitrary way. We can just have a grid. We can start looking at that. Then we can simplify it even more. We can actually go and say, instead of having continuous numbers that represent the activations in this neural net, let's just say that we have a neural net, but it isn't really a net, it's just a grid. And at every cell in the grid, we pick one of two rules, one of two friendly little cellular automaton rules. So here are examples of grids which the different colors at different cells in the background represent which of the two rules we're picking. And so with one rule, the thing just makes a stripe here. When you pick different rules at every cell, it makes this nested pattern. Here it's making this more complicated pattern, and so on. So essentially, our minimal machine learning system now is just this grid, this inhomogeneous cellular automaton that has one of two possible rules at each cell, at each site in the space-time, so to speak, and we're then just looking at we're just sort of evolving on top of that background. Okay, so now let's imagine that we do sort of a machine learning kind of thing. Let's say that we try and learn to live for exactly 50 steps. And we do that by flipping bits in this background, by just changing which rule occurs at which site. We just keep doing that, keep flipping bits, and eventually we will successfully machine learn, so to speak, how to live for exactly 50 steps. So this is now sort of a minimal version of sort of what's going on inside a neural net-like system. And so one thing we can ask is, well, then we can look, this is the, well, this is drawn as a fitness curve. It would be a loss curve if it was machine learning and turned upside down. But this is showing how we succeed in living for different numbers of steps. We can look at sort of other kinds of machine learning problems. But here, let's just look at this particular problem. And let's ask, what are some different ways it could be solved? We're just rolling the dice different time, doing different mutations, and we see different solutions to this problem. Some of them are quite easy to understand. Some of them is doing all kinds of complicated things, but then it happens to give the right answer. Well, we can do the same thing with other machine learning kinds of problems. This is, what's this one? This is, I think, what is this one? Let's see, I think this is, okay, this is one where it's learning that function that I showed you at the beginning. Depending on where the initial bit is placed, the final bit will end up at a position that corresponds to either +1 or either 0 or 1. So this is, again, this is a picture of what's happening inside machine learning, something one hasn't really been able to see before, but in this extremely simple model, you can see sort of what's going on. Well, what is going on? What's going on is, again, a story of computational irreducibility. It's what, and my picture now of machine learning is this, that machine learning is kind of recruiting lumps of computational irreducibility to do what it wants to do. So you can kind of think of it this way. Let's say your objective is to build a wall. Well, one way to do that is you make bricks, and they're all very nicely shaped, and you arrange them in a nice bricklayer pattern. But an alternative is you see a bunch of rocks lying around on the ground, and at every step, you sort of pick a rock that more or less fits into the space you have in the wall, and you progressively build up that stone wall. Well, that second thing is what's happening, is sort of an analogy of what's happening in machine learning. In machine learning, you are, in the training process, you are recruiting lumps of irreducible computation to form the thing that you want to achieve. And thinking about it that way, you realize that if you ask the question, well, why is the machine learning system arranged just that particular way? There isn't going to be a good answer to that question, because it's just like, well, it's because those rocks happen to be lying around on the ground. So that's kind of a picture of what's happening in machine learning. I might say that this sort of picture in the practicalities of machine learning, in my sort of day job, what I'm concerned with is trying to make our computational language, our Wolfram language, represent kind of things in the world computationally. But the things I'm trying to make it represent are things that we humans care about, like math, like cities, like geography, things like this that we humans care about. And the kind of the thing that's sort of emerging very nicely is that there's this kind of, we have been able to make this kind of computational language to represent precisely many kinds of things in the world that humans care about. And we've been able to sort of get that system to be able to do precise computations in that area. And the thing that sort of emerged as the workflow is you use the neural net, the large language model, whatever, as your linguistic user interface. You just talk to it, you say vague things, and then you get it to generate a sort of a precise specification in Wolfram language of what you want to compute. Then you do that computation precisely. You're kind of building a precise brick of computation. Well, the machine learning system has all these misshapen rocks that happen to be able to be fit together to do something useful, and something that we can do things like generate useful language and have conversations and so on. But when you want to build something that's systematic, you end up having to use that to generate these kind of bricks of precise computation. And that's kind of the story of what we've been building for the last 40 years, that now has not only lots of human users, but also lots of AI users using Wolfram language as a tool, just as humans use it as a tool to build those sort of precise bricks of computation. Well, I mentioned a couple more things, and then I'd love to have whatever discussion people are interested in. I can find my mouse here. There we go. Let me talk about a couple of things. One thing sort of interesting is thinking about the Roolead. I've talked about the Roolead and observers and so on. And one thing I've been very interested in is the question of what are observers like when they're not like us? And so one nice experiment you can do is with generative AI system where you're doing image generation, for example, and you say, well, generate me a picture of a cat in a party hat. But now you imagine going away from the point in kind of AI space that corresponds to a cat in a party hat. You go away from that point. You move away from that place in embedding space, and you say, what's around the cat? What's the kind of island of concepts around the concept of a cat? So this is one projection of kind of cat island. And what you realize is that there's this whole space of all sorts of different kinds of structures out there in the kind of universe of possible things that an AI can think about, so to speak. And only a tiny fraction of them are ones that we currently have words for, we have concepts for. The way I think about it is, in this kind of possible space of, for example, images here, we can think about most of it as interconcept space, just like most of space is interstellar space. But occasionally we'll get to the place where we have a concept. And we might have 50,000 concepts, 50,000 words in a typical language. There are, those are our concepts, and the rest is filled with interconcept space. And in a sense, the way the concepts we have represent an absolutely microscopic fraction of the space of all possible concepts. And in a sense, the progress of human thinking and development is the progress of kind of expanding out in interconcept space, gradually expanding the set of concepts we have. Interestingly, ruleology is a field that allows you to jump anywhere in this interconcept space. You can just pick a rule and you jumped to somewhere, some sort of arbitrary place in interconcept space. And the challenge there is not to make that jump. The challenge there is to understand what you've got when you went there, so to speak, to be able to make that link to sort of human concepts that we care about from things that you just find out in the Ruliad and can explore with ruleology. Okay, well, I'll just mention a thing that I just worked on last week, talking about applying some of these ideas. This is an application to medicine. Let's see if I have that. Here we go. So we're starting off with, we say, well, what's a minimal model? What's a sort of formalization of what's going on in medicine? Well, you got these critters like us that are evolved, and they're evolved, for example, to have a certain robustness, but they're evolved, they do what they do. Well, now let's imagine that we perturb that critter. So this is what it normally does, but this is what happens if we kick the critter, we flipped a bit in the critter. It doesn't live as long. It effectively has a disease. These are different diseases that this organism could have that come from different perturbations that happen to the organism. And so then we can kind of ask the question, well, this is sort of our model we can ask all kinds of questions about this. If we make our model for an organism to be this thing that was evolved to have certain characteristics, and then we say, well, what happens when we perturb that organism? What kinds of diseases does it get? And so we can kind of lay out a space of possible diseases. We can make a hierarchy of them too, but we can lay out the space of possible diseases, and we can ask questions like, are there only a finite number of diseases? Do diseases cluster? Can we identify separate diseases, or will there always be kind of these links between diseases? That's an example of a kind of question you can start to ask. We can ask, what's the mortality curve for these organisms? It doesn't happen to be a Gompertz distribution, but we can ask, as we perturb these organisms, how does that change their lifetimes? So then we can say, well, what are we trying to do in medicine? In medicine, what we're trying to do is, some perturbation happened. Now our goal is to find a treatment perturbation that we can apply that will make the organism go back to either more or less what it was doing before, or at least live a happy life for the same kind of time, let's say, that the other organism lived. And we're not representing here the details of what happens in any particular biological system. The goal is to find kind of a conceptual way of thinking about the problem of disease, the problem of medicine, so to speak. It's kind of like, if you're thinking about biological evolution, you can just say, well, think about biological species, you can just say, well, there are all these species that happen to be around. But it is a useful organizing principle to start thinking about natural selection and mutation and so on. And the goal here is to have a similar kind of foundation that comes out of sort of these computational ways of thinking about things, for thinking about the problem of medicine. And there's lots that you can do here. You can start thinking about different, can you use machine learning to predict what will happen in the system? To what extent can a coarse-grained symptom predict what's going to happen? Those kinds of questions. And you can start asking questions about what's the effect of effectively genetic diversity on the outcomes and so on. And there's all sorts of interesting things to look at. I just kind of started this, but the point is that what one ends up seeing is, again, these stories of computational irreducibility and the fact that in a typical perturbation has sort of computationally irreducible effects on the organism. It's not easy to predict what will happen when you make that perturbation. And then if you try to figure out, well, how would you treat that perturbation? It's, again, some stories of computational irreducibility. What one sort of hopes for is enough computational reducibility that one can kind of predict what to do. All right. Well, that was a very quick survey of a few things that both from the distant past and from much more recently that I've been thinking about related to sort of questions about complexity and sort of how it plays out and this interplay between computational irreducibility as this fundamental underlying phenomenon and our role as computationally bounded observers and the kinds of laws that we can deduce on that basis. All right, I should stop there, and I'm happy to try and answer questions that people might have.